Good morning. For Lab 5, we'll be using an incline plane to calculate the theoretical acceleration of the glider, and we'll be adding some mass. We'll be analyzing and calculating how much the theoretical acceleration changes. It should not change that much since we're going towards the gravity. So the steeper the object is, the faster it will go. So in our case, we'll be changing the mass, but we're going towards the gravity, and this is helpful in real life. So, an example, if you're going on the highway and you're driving through a bridge, you can calculate how much acceleration you're gonna have if you're going against the gravity, because gravity is gonna decrease your velocity, and if you're going towards the gravity, you're gonna be faster because you're going towards the gravity, and the steeper the object is, the faster you will go. For materials, we'll be using our motion sensor as in our previous labs. This is going to help us determine and measure the motion of our glider, which is this one that we previously used in the labs. The difference in this lab is that we'll be adding this mass, and we'll be changing it and measuring and analyzing how much the theoretical acceleration changes. And also we're going to be using this little object. This is going to help us create an inclined plane and do an angle, so we can also calculate that and see how much, like the steeper it goes, the faster it will go, and calculate our theoretical acceleration. And we'll be using our sensor, our software as usual, and we're also going to be using our interface.
For lab 5, we had to make an angle first. So in order to do that, we added these two. These were, I believe, 0.002 meters, and then from the middle to the end, it's a meter. So we have our hypotenuse and then our starting point. And then the sensor, we had to bring it up a little bit more, so in order for it to calculate it right, so we use the little weights. And then we just start at the middle, and then we let it go and let the graph calculate it. And the graph gave us these. So this is our position versus time graph, and this is our velocity versus time graph. The position was very smooth all throughout, and then the velocity changed a little bit more, but yeah, we were able to calculate it from there.
After running our first experiment, we're going to be interviewing our scientist, Gabriela Ruiz. So my first question to you is, are you expecting a different acceleration? Why?
We are not expecting a different acceleration. If there is any change, it's going to be very little, but there should not be a drastic change since the mass doesn't really apply to the acceleration.
My second question to you is, are you expecting a different percent error? Why?
There should be a slight change of the percent error just based on the amount of force that we use to push the glider, which will affect the velocity, and it will affect the acceleration, which will affect the percent error.
So we're going to make a second run, but with a little change, which is the mass of the glider. We're going to put some mass on this glider, and we're going to run the experiment with this mass. And we're going to have a position time graph, which is the first one, and it's going to give us a velocity time graph, and we're going to have two velocities. Our initial velocity is 0.33 meters per second, and for our final velocity we have 0.22 meters per second. Ahora sí hacer.
For part 3, we went from having a high tilt to having a low tilt, and to do that, we took off one of the objects that we placed in order to make the angle smaller, and then we kept the weights onto the glider, and which caused us to have, it shouldn't change its acceleration, but the graph gave us a different position or velocity, because the position didn't change as much and the velocity didn't change as much either. So the graph didn't change a lot, and the velocity, our initial velocity was 3.1 seconds, and then 0.41 meters per second, and then our final velocity was 7.05 seconds with 0.23 meters per second.
For the third part of our experiment, we'll be also interviewing our scientist Gabriela Ruiz. So my first question to you is, which experimental acceleration had the most significant percent error?
The acceleration that had the most significant percent error was our first two tables, which was the low mass and high tilt and the high mass and high tilt. Those had 85% errors, and our low tilt had 66% error. So the first two were the ones with the highest percent errors.
My second question to you is, which acceleration had the most unexpected value?
I would say neither, just because it all depended on the amount of force in which we pushed the glider, and it made sense to get such a low value because of our meters per second.
Thank you.
I will be explaining the data that we retrieved from our experiment today. So here we have our first calculation, which was to find the sine of theta, and to calculate that we had to get the height, which was our opposite, and it was 0.02 meters over 1 meter, which was our hypotenuse, and we got 0.02. So with that, we calculated the theoretical acceleration. So with the 0.02, we multiplied that by the gravity, which is 9.8, and it was 0.196. So with our first table, as you can see, it was just our opposite, which was our 0.02, our height, and our hypotenuse of 1 meter, and our sine theta, which we got previously, was 0.02, and our acceleration was 0.196. And then our second table was the experimental acceleration 1, which was the low mass and high tilt, which was our 0.02 height and no mass added. So our initial velocity was 0.55 meters per second at 1.400 seconds, and our final velocity was 0.41 meters per second at 6.350 seconds. Our experimental acceleration using these values was negative 0.3, and our percent error was 85% using our experimental acceleration and our theoretical acceleration. Now with our table 3, this was our experimental acceleration 2 that had a high mass and high tilt, and that was using the same opposite, meaning the same height that we had added, but then we added an additional weight onto our glider. So our initial velocity when we did the experiment was 0.33 meters per second at 2.850 seconds, and our final velocity was 0.22 meters per second at 6.300 seconds. And I calculated the experimental acceleration, and that gave us 0.03, and that was negative, which was the same experimental acceleration that we had gotten before, which makes sense because the mass doesn't affect the acceleration that we had gotten, and the percent error was 85% again. And our next table, which is table 4, theoretical acceleration 2, which was the low tilt, that was decreasing our height and our opposite, and our opposite this time was 0.015 meters instead of 0.02 meters, and our hypotenuse stayed the same, 1 meter, and our sine theta this time was 0.015, and using that, multiplying it by the gravity, gave us a theoretical acceleration of 0.147. And the percent difference between our theoretical acceleration here and our theoretical acceleration from before was 25%, which is not a big difference. And performing the experiment gave us table 5, which was the experimental acceleration low tilt again, and our initial velocity was 0.41 meters per second at 3.100 seconds, and our final velocity was 0.23 meters per second at 7.050 seconds. And our experimental acceleration was negative 0.5, which was not a big difference from our experimental acceleration without the mass. So that was just a 0.02 difference. And then our percent error using 2 with 3, meaning using the acceleration, the theoretical acceleration we got before and our experimental acceleration that we have now, was 66%, which is a less percent difference than what we had before with the high tilt.
So for conclusion, we're going to answer some questions related to our experiment. And for our first question, we have which experimental acceleration had the most significant percent error? And the acceleration with the most significant percent error were the first two, with an 85% error. And that's because we just changed for our second run, we changed the mass of the glider. And as we know, acceleration and mass are not proportionally related. So that's why we got the same acceleration with the same percent error. For our second question, we have which of the accelerations had the most unexpected value? And actually, none of the accelerations had an unexpected value, and here's why. The first two accelerations we knew that they were going to be exactly the same, or the acceleration might just change a little bit, and that's because we just changed the mass of the glider, and we know that the acceleration it's not proportionally related to the mass. And for our third run, we changed the angle, and we know that the acceleration of an inclined plane, if we change the angle, the acceleration is going to change. And as we decrease the angle of this inclined plane, our acceleration had a lower value. And so in conclusion, none of the accelerations that we got of our experiments were unexpected values. In the end, we learned that acceleration and mass, as I've been saying, they don't have a direct relation between them. So that's why in our first two runs of the experiment, whenever we changed the mass of the glider, the acceleration didn't change. And that's because they don't have a direct relation between them. And we learned that whenever we change the angle of the inclined plane, the acceleration will change. And that's because they do have a relation between them, and that's why whenever we change the angle of an inclined plane, the acceleration will change.
Okay, I was in charge of setting up the whole experiment and to record some of the videos that you're watching right now.
I was in charge of recording the data and making all of the tables and the calculations, and of playing the scientist.
I was in charge of helping setting up the experiment and making the graphs.
I was in charge of editing this video and recording some of the frames, and I was also in charge of playing the reporter.